In this week's lab, we'll be looking at simulation modeling using a model of even-aged forest management that is similar to models we've been using before for the linear programming labs. However, we are not going to be linear programming this in this lab for reasons that I will explain as we go along. So the objectives of the lab are to describe the evolution of forests over time when it's managed according to a variant of area control. You will also be asked in the problems to adapt this model to use a variant of volume control. We want to be able to predict the effects of changing the allowable cut on net present value and carbon stocks, and this will also include some looking at what optimal rotation age is when you have various discount rates. We're going to determine how the economic rotation changes when harvest influences timber prices. So if you are a big enough producer that the amount of timber that you produce will actually change the price in the local market, you may have a different strategy than a producer whose level of production doesn't have any impact on the prices in the market. And we'll see how that works as we go through here. And then we want to move in and look at stochastic simulation, where we can take into account some of the risk that are associated with uncertain events, fires, windstorms, perhaps prices that vary over time. And we're going to look at how to develop best management policies in the context of risk and uncertainty. Again, to date, we have in our labs, certainly, we haven't really contemplated what risk and uncertainty does to optimal management practices, but it does have an impact, and this is something that both in my lecture for this week and also in some of the papers that you're reading for this week, you will see. Before we launch into the model itself, I want to just talk for a minute or so about the difference between optimization and simulation, and then also between deterministic simulation and stochastic simulation. So we have used optimization, linear programming, for quite a number of labs over the course of the semester. The idea behind linear programming is that you are trying to find the most optimal solution possible. And that's given your constraints and the setup of your model. Now, that is a noble aspiration, but it does limit how you can set your models up. You need to set them up in a way that allows for there to be constraints programmed in a particular way, and that looks at having one thing that you are optimizing. Now, as we've seen in those optimization labs, sometimes you can vary your constraints. You can look at optimizing different variables, but those models are fairly rigid in how they need to be set up. Simulation is what we've been doing when we've been doing FVS labs. There's a lot more flexibility in that modeling system. And it may allow you to get a better sense of what the decision space is that you're operating in. And so we are going to be developing a model that is similar to something we've used for linear optimization, but we're not going to be optimizing it. We're going to be looking at various effects of various management decisions and such. Now, the second piece I want to talk about is the difference between deterministic simulation and stochastic simulation. So deterministic simulation occurs when you set up a system, and if you start with the same starting conditions, you will always end up with the same outputs. Now, FVS is basically a deterministic simulator. It does have some ability to incorporate some stochastic elements, but generally speaking, people tend to turn those off or not implement, not call on them. And so it gives you one answer if if you treat this stand using this particular prescription, you're going to get this particular result, and then growth is going to happen as growth happens. And if someone else treats it the same way, they will get the same result. Stochastic simulation allows you to take into account variability. And in the context of this lab, we are going to use stochastic simulation to do two things. First, we're going to use stochastic simulation to look at what happens if you have a disturbance that has a possibility of occurring every year. You know what the disturbance return interval is, and you have some sense of how severe that disturbance is, and you can model those things because you have a probability distribution with how often does the disturbance come through, and you have a probability distribution associated with how intense is that disturbance when in fact it does come through. How much of the timber does it destroy? We're also going to be looking at variations in timber prices. And so it may be that you know on average what the timber price is, but that may change from year to year a little bit. It may have some fluctuation there, and you can look at how that change in price might affect your optimal decision making. If you know that price changes are occurring over time, you might make different decisions. I suggested in my lecture lab, or my lecture, that actually if you are a canny forest owner and you have the ability to be flexible about when you harvest, you can actually do better in terms of your net present value by harvesting more when prices are high and less when prices are low. And you can do that because you may be able to make a prediction about, our price is higher than average this year or lower than average, and how should that affect, how I harvest. But you need to know what the average is. You need to have some way of determining if this is sort of outside of the normal average that you would expect. Okay, so let's get started and let's talk about the model for this. This is similar to a model that we've used for even-aged management several times with the linear programming. We are going to assume that we have 4 age classes. And so we have age classes with state variables of A1J, A2J, A3J, A4J. The 1, 2, 3, 4 in this case refers to age classes, which we are going to be using as 10-year age classes. So A1 is going to be forest land that is between 0 and 10 years. A2 is between 11 and 20, and A3 between 21 and 30, A4 between 31 and 40 years. If we want to know how those age classes are going to change over time, we can model it this way. And we've in fact done that in a prior lab where the amount of area in age class 1 in time t plus 10 years later is going to be the amount that was cut in each of the 4 age classes in the prior period. The amount that is in age class 2 is going to be equal to the amount that was in age class 1 in the prior period, minus the amount that was cut in age class 1 in the prior period. Age class 3 is similar. It's the amount that was in age class 2 in the prior period, minus the amount that was cut in age class 2 in the prior period. And then age class 4 is the amount that is in age class 3 in the prior period, minus the amount that was cut. And then you only have 4 age classes. And so actually the 4th age class is 31 and above. So anything older than 31 gets lumped into the 4th age class, the oldest age class. Okay, so this should look familiar to you. We've done a model like this before. Now, we're going to first assume area control, and that's how we're going to determine our cut. And so we're going to decide what our rotation age is. So this could be 10 years, 20 years, 30 years, 40 years. And the amount that we can cut in any 1 year is going to be the sum of the total acreage in our forest. And so in a moment, we're going to be looking at a forest over here that has 500 acres in it. And so if you have 500 acres and you're going to manage it on, say, a 50-year rotation, you could cut 10 acres per year. 500 acres divided by 50 is 10 hectares per year. Our time step is going to be 10 years. And so if you're doing a 10-year modeling time step, you take your 50 acres per year, you multiply it by 10, and you can cut 500 acres. Just a second, I'm doing that math in my head. 500 divided by 50, there we go, 10 acres per year. And if you are doing that for 10 years, you can cut 100 hectares in a 10-year time period. Okay, so that's what this is telling us. And then we're going to set up the model so that the area that gets cut is always going to be the oldest age class first. And so the amount that is cut in the oldest age class is going to be the minimum of the allowable cut, or I'm sorry, the minimum of what is in that age class or the allowable cut. Okay, whichever, because you can't cut more than you have. And so the amount that you third oldest age class is going to be the amount that is the minimum of the amount that is available in the third oldest age class, and the allowable cut minus whatever was cut out of the oldest age class. What's going to be cut in the second oldest age class is going to be the minimum of either what is in that age class or what is left over that hasn't already been cut out of either age class 4 or age class 3. And then finally, the amount that is cut in age class 1 is going to be either the minimum of what is available in age class 1 or whatever has been cut in these other age classes, or whatever has not yet been cut out in those other age classes. Okay, so let's look at this and see how that works out. So in this case, we are, let me make this a little smaller here, maybe. There we go. Okay, so okay, here is our allowable cut of 83 acres here, and we got that by summing up our total acres, which should have been 500, and then dividing it by a 60-year rotation here and multiplying it by 10. And so that says that we can cut 8.3 hectares per year, or 83.3 hectares in a 10-year period. And so here then we look at what's happening, and we're going to cut it out of this age class, and we cut either the minimum of our total allowable cut or whatever is available here in this particular age class. And so it turns out that in this case, with a 60-year rotation, we are always going to be cutting out of age class 4. Now, if we cut our rotation age down to, say, 20, notice that this is a fairly old forest with a lot of hectare acreage in the oldest age class. And so if we cut it down to 20, ultimately, we should be moving towards a forest that has a rotation age of 20. And so you'll have forest land in age class 1 and age class 2 eventually. Okay, and so what we see here then is if we are going to have a 20-year rotation, we're going to cut 250 hectares per 10-year period. And when we look at this, what happens in the first period is we have 300 hectares in the oldest age class, and we're going to cut 250. And so we cut 250 and we're done. And these other things still give us 0 cut because here, this is 250 minus the 250 that's been cut here. Okay, down here then, and the second period, we cut this from 300 down to 50. 50 remains in the 4th age class, and then 100 hectares grows up into that 4th age class. So we end up with 150 here. This is 50 because it's the 2nd age class growing into the 3rd age class, and this is 50 because it's the youngest age class growing into the 2nd youngest age class, and this is 250 because this is the 250 hectares that we cut. Now, in this case, in year 10, our second time period, we are trying to cut still, again, 250 hectares, but we only have 150 hectares in that oldest age class, so we cut it. And then we go to the second oldest age class, and we see that we could cut 250, but we've already cut 150, so we could cut up to 100 hectares in the third oldest age class. But there's only 50 hectares to cut, and so we cut that. And then we come here and we've cut 200 hectares so far out of our allowable 250, and so there's 50 here to cut, and we're cutting 50. And then in the third period, we have got this into a state of regulation, and all we have left is 250 hectares in each of 2 age classes. And we could, change it to say a 25-year rotation, and we'll see that when we have a 25-year rotation, we end up cutting some out of the 3rd age class and some out of the 2nd age class when we get to sort of our steady state. Okay, so that's how that works. We'll set that back to 60. Then let's talk about financial performance. So with financial performance, we need to know a couple things. We need to know how much volume we are harvesting in a given time period. That volume is going to be dependent on how many acres we harvest in each age class by the yield that is available in each of those age classes. And so we can see that happening here. And so here is our yield stream. We think that we're going to have 50 cubic meters per hectare in the youngest age class, 120 in the second youngest age class, 260 in the third youngest age class, and 400 in the oldest age class there. Okay, and so again, that should look relatively familiar. And so we're going to see when we do the sum product here, we are getting the number of acres that we're harvesting times the amount of volume in each one of those age classes. Okay, and so on down here. And each time it turns out that we are harvesting we're harvesting 33,000 cubic meters. Note that I've done a conversion here. I've divided through by 1,000 because this is cubic meters per hectare. And when we multiply that, we get a pretty large number for cubic meters. So we're dividing it through by 1,000 to get a volume in 1,000 cubic meters. So 33,000 cubic meters being harvested in each 10-year period here. Our net periodic income is going to depend on a couple things. It is going to depend on, first, the value of our harvest. So P is going to be our timber price per unit volume. It's like a stumpage value. And we are going to have a value of $50 per cubic meter harvested. So there's our stumpage. And then we are going to subtract a management cost associated with reforesting our stand. And we're going to assess a $500 per hectare reforestation cost. And so that's what this equation is doing. We are taking our volume here, we're multiplying it by our value per cubic meter here, and then we are dividing, or excuse me, subtracting, there we go, the sum of the acres that have been harvested times the value that we have harvested, and we are going to divide this through by 1,000 to get our value in $1,000 here. And so notice that we don't have to divide this through by 1,000 because we're already expressing this in 1,000 meters cubed, but we're multiplying it by a value that's been provided in dollars per meter cubed, not dollars per 1,000 meter cubed. So we could have, multiplied this value by 1,000 and then divided everything by 1,000, but we're not going to do that. And so what we see here is that the net value of that first harvest is going to be $1,625,000 or $1.625 million. The net present value, then, we are going to calculate as we've done net present value before. We're going to be doing it for each individual time period. So here we are discounting using a 5% discount rate for 0 years. And so when you take 1625 and you discount it by 0, it's still 1625. By 0 years, it's still 1625. The second value here is going to be discounted by 10 years. And then, when you get up here, you're discounting by 70 years at that 5% discount rate, and it's getting less and less. And we are running this simulation for 100 years. Notice that by the time you get out to 100 years, that value of that $1.6 million is only worth $12,000 when you discount it. You could go, further on and, go to 200 years if you were really concerned. But that $12,000 out there, the next one is going to be maybe $5,000. So basically we're ignoring any revenue, the net present value of any revenue that comes in after 100 years. You wouldn't have to do that, but it just makes the spreadsheet longer if you do, and it doesn't have a huge impact on the value. All right, and so if we want to know the present value of this, the net present value of this kind of management regime, it's right here. It's $4,189. And so in prior labs, we've looked at, trying to optimize this value, maximize the net present value based on different management regimes. We're not going to try and optimize it now, but we could look at this regime and we could compare it to another regime where we use a different rotation age. Let's say, look at that 4189. If we change it to a 30-year rotation age, notice that this has gone up. So a 30-year rotation is more economically optimal than the 60-year rotation. And we could look at other rotation ages. 20 years is even better. Okay, and so we're looking at that, and we could, as we've done before, calculate an opportunity cost related to, the difference between using a 60-year rotation age and a 20-year rotation age or 30-year rotation age. All right. Okay, and so down here, the length of time, T, in this case is 100 years. But again, we could run the simulation out longer than that. All right, next, let's talk about carbon storage. And this is going to be a relatively simple model of carbon storage. It's basically assuming that this is a single species stand, and it's assuming that the the cubic volume of the stand is a good proxy for carbon. There are some variations that you might take into account based on, if you want to know the volume, if you want to truly know the total carbon stock, you would need to take into account, what's in the branches and bark and leaves. And this is not doing it. It's just looking at the wood. Whatever, gets classified as harvestable wood, that's where we're going to get our carbon estimate from. And based on assumption here about the tons of carbon per cubic meter of wood, this is something that would vary if you had different species, and you could certainly develop a model that would do that, but it's going to be more complicated. So as a simplifying assumption, we're going to assume that for each cubic meter of wood you have 0.65 tons of carbon, and that's related to the density of the wood. And so here we can get our carbon here. We can look at the carbon that is standing in the forest. And so it's going to be based on the acres in each one of these age classes times the volume of wood in each one of these age classes times 0.65 to convert it from cubic meters of wood cubic meters of wood to tons of carbon. And so here you see that we start with 100 tons of carbon approximately in this forest, and we gradually bring it down to 88 tons of carbon in this forest as we move this forest into a regulated condition. The regulated condition in this case with a 50-year rotation age, or with a 60-year rotation age, excuse me, is to have 83 acres in each one of the young age classes, and then 250 acres in the 31 and above age class. Okay. All right. So here is our spreadsheet. I've gone through that spreadsheet, so I don't think you need to don't think I need to do more on that. Notice that the equations that are being used here are down here. For this particular exercise, I am not going to ask you to code this in. I'm just going to give you the model already coded. And you're going to adapt it as you have done before. Just there's a lot going on here, and I think you've had plenty of experience at this point of converting from written equations into the formulas in Excel. So I don't think you need more practice on that. We want to look at what are the implications of the model more so than coding the model in this particular exercise. All right, so now let's look at the effect of different rotation ages on the net present value and the carbon content. And this is going to be a new tool, I think, for most of you in Excel. So I'm going to walk through how this gets set up, because you're going to need to do some of this piece. You're going to need to adapt this method in some of the questions for this week. So the first thing you're going to do when you set up a table like this, what it's doing is Excel is iterating through different rotation ages and telling us what the net present value is if we use a different rotation age, and then also telling us what the carbon content is if we use a different rotation age. And so what you are going to do here is you set up your table, you set up your column headings so you know what's going on, and you can set up your rotation ages here so you know what rotation ages to look at. And here you are going to set this cell equal to N15, which is where we've calculated the net present value of the 100-year simulation. And then you're going to set this cell to the carbon that we see in that forest at year 100, once it's basically reached a steady state. So that's step one. Step two when you're going to set this up is you are going to select R6 through R12, or I'm sorry, through T12 here. And you need to then, I have to make this one bigger. You need to go into data, and you need to go into what if analysis data table, and your row input is going to be I believe you can ignore it. Your column input is going to be cell I16. Here, and so that's telling you that you're gonna vary this variable based on these numbers to get the outputs that are coming out here. Okay, and that should work, except that I need to get rid of those. Okay, and there we go. And so that should have recreated the table I just had. And I need to adjust this because, in fact, it's not the data menu. It's under the what if analysis. So I'll adjust those. Okay, so there it is. And so then what this is telling you, and that's the important part, how to do it is kind of cool, but what it's telling you is more important, which is if you look at this, you can see when approximately anyway, when net present value is optimized. And given this discount rate, given these this structure of costs and revenues, the optimal economic rotation age here is 10 years. But notice that the amount of carbon there is pretty low compared to what it could be if you had 100 years. And so if you wanted to, if you were interested in looking at potential impacts of having a carbon price, for example, and giving people a certain amount of money to sequester a certain amount of carbon in their forest, you could certainly adapt this to take into account some sort of value on that carbon. And that might encourage them to have a longer rotation age if they did that. And it would ultimately get accounted for in this net present value. Okay, but in any case, you can see that graph here then as rotation age goes up, the net present value goes down, probably what you expect. And then as rotation age goes up, the amount of carbon in the standing forest goes up. Again, that's probably what you would expect. All right, so there is that. Now, next complication. We have generally assumed that the amount of volume that an individual landowner cuts does not affect the timber price. And that's a common assumption in a lot of economic models. If you have a lot of small producers, that is probably the case. Sometimes in forestry, you may have a large producer and the local mills have limited capacity. And also the local market may have limited capacity to absorb the demand. And so when that happens, an individual forest owner can actually influence the market. And if they sell enough wood, if they cut enough wood, that will actually drive the timber or the price down. And so that's what we're going to look at in this next exercise. And so we are going to assume that there is a downward sloping demand curve. So if you've taken economics, you may, have seen this in a downward sloping demand curve and an upward sloping supply curve. And where demand and supply cross each other, that's sort of the equilibrium in those economic models. And basically what that downward sloping demand curve means is that as price goes up, the quantity demanded is going to go down. Because, if a new iPhone is only $200, a lot more people are going to buy them than if the new iPhone is $1,200. So similarly with timber, as the price goes up, the demand for timber is going to go down. And so we're going to set that up as so. The price here in a given period is going to be equal to A, which is a coefficient we'll get to in a moment, or a parameter that we'll get to in a moment, times the amount harvested raised to the negative 0.7. And basically what this equation implies is that as the volume harvested goes up by 1%, the price that people are going to get for that volume is going to go down by 0.7%. Or alternately, you can look at it the other way. A 1% increase in price leads to a 1.43% decline in demand. Okay, so if price goes up, demand goes down. And if the volume harvested goes up, the price will go down. All right, and we say in this case that timber demand is elastic with respect to price. People will demand more or less based on what the price is. So to estimate parameter A here, we need to know the price for a given level of harvest. And we are going to give it to you for this exercise. And we're going to say that if the harvest is 30,000 meters cubed in a 10-year period, then the price is going to be $30 per, let's see, $30 per meter cubed. Okay, so we can plug in our we can plug in, and I see I have another typo here, which I'll have to correct, and I will correct it on the version that is up on Moodle, so you'll see it there. But in any case, I'll have to double check this. When you plug in these numbers here, I think the price is actually supposed to be 50. You can solve this equation. So you're going to take 50 and you're going to divide it by 30 raised to the negative 0.07. And so let's do that. 50 divided by 30 raised to the negative 0.7. And you will get then A is equal to 541. I've rounded that. It's actually 540.69, but we'll round it to 541. And so this is now going to allow us to predict a price based on the volume being harvested using this equation. Okay, and so we will see that here. And so here we go. It's going to be 541 from here times a quantity here that is being harvested of 10,000 cubic meters per 10-year period up to 50,000 cubic meters per 10-year period. And we are taking this quantity and raising it to the negative 0.07. And so what we see is this downward sloping demand curve. As price goes up, the amount of timber demanded is going down. All right, so if the price were say 110 or so, the quantity that you're going to be able to sell into the market is 10,000 cubic meters. At a price of, if you want to sell 50,000 cubic meters into the market, you're going to have to accept a price of around $35 per cubic meter. Okay. The main point here is the more you try to sell, the more it's going to drive that price down. So you're going to get less revenue per unit sold. Maybe not less revenue total, but less revenue per unit sold. Okay, so there is that. So we can take this into account and we can build into our model a price that is based on the amount that we've harvested. And so okay. And so we are going to take our volume harvested here. We're going to multiply it by a price over here. And we are then going to subtract the cost of reforestation here. And the main thing that's been changed here is this price, and this price is going to be based on our demand here times the amount harvested here, raised to the negative 0.07. And this demand is so I've set this up to take into account the harvest here, and then this is the equivalent of the value here, 541, and apparently I was messing with this, so if I put 541 in there, then that will adjust the price to the appropriate level. But you may be called upon to change this coefficient here to something else to see how it affects the demand and such. Okay, so here it is. And you can see that if I were to change the rotation age to say 20, notice that that price changes over time, because while I'm harvesting 250 acres in each time period, in the early time periods, harvesting 250 acres results in a much larger amount of volume being harvested, and therefore it drives the price down. In the later time periods, you're harvesting a relatively small amount of volume, and so the price goes up for that. And that will affect then the net present value. We'll go back to 60. And so if you look at this, then you can compare what happens when price is inelastic, which is to say that you can sell as much into the market as you like at a given price, and it doesn't matter if you sell a lot or a little. Your operations are just not large enough to affect the market price, and that is here. And so in that case, the optimal rotation age is here at 10 years. Now, if you look over here, and you can set up your calculation here, similar to how we did it for the previous inelastic demand, you will see that the optimal rotation age actually increases to, looks like 30 is just slightly better than 20. And so the optimal economic rotation age increases. And the reason for that is that by harvesting a little later, you are able to get a capitalize on a price difference. Yeah, price difference there. Okay. So if your harvesting level actually affects the price, you may have a different decision to make than if your harvest level does not affect the price. All right. Now, let's think about modeling storms. And if we model storms, we are going to look at the probability of having a storm, and we can use this probability distribution here. So this is the probability of a storm occurring within a certain number of years. And in order to do this, we need to have a time here, and we need to have a disturbance return interval. And so in this case, we're going to assume that the disturbance return interval is 25 years. And that's saying that on average, we expect a storm in this case that is going to cause significant damage to the forest to occur about once every 25 years. This is the same thing we could do with, say, a fire return interval of, once every, 50 years or something. And so then when we simulate this, we can look and say, okay, if on average we have a storm once every 25 years, there is about a 33% probability that we'll have a storm in 10 years, and there is a close to 98% probability that we'll have a storm at least once in 100 years. And so that's what that's saying. And then what we're going to do to make the stochastic is we're going to draw a random number. And if that random number is greater than the probability of having a storm, we are going to assume that a storm has occurred. Okay. So we can look at that here. And now we're setting this up a little bit differently. And here's our storm modeling. And so here's our storm modeling. And so, and actually, less than or equal to that. Okay, so this is saying that it's going to generate a random number. And if that random number is less than or equal to this equation, the probability that you will have had a storm then you will say that you had a storm, otherwise you will not. And so here it looks like in this simulation, there's a storm in year 10, there's another storm in year 90, and another storm in year 100. Okay. And then we adjust this to take into account the loss. And on the loss, we are going to assume that there's only going to be a loss if, in fact, there was a storm. And so if there wasn't a storm, this gets to be 0, and all of this becomes 0. But then we are going to, when there is a storm, we are going to take a random number between 0 and 1, again, and that's what this rand does. And we are going to assume that this is the amount of damage that has been done to that stand. And so we will take the amount of area in that age class, and we're going to subtract whatever was cut in that age class, and that's going to give us what remains in that age class. And what remains in that age class, we're going to assume a certain amount of it got destroyed by the storm, and it's basically on those acres. It's basically a stand replacing disturbance. Okay, but what that means then is we are going to need to adjust our growth model here. And so our growth model is going to need to take into account both what we cut and whatever acreage here has been destroyed, which is going to be some subset of the, when there is a storm, subset of the acreage that has happened, that has been hit. Notice that we are assuming with this model that all age classes have the same probability of getting hit by the storm. And while the amount of damage in any age class in any period might be a little bit different, so the proportion damage might be a little bit different, that they all have the same probability of being damaged. This may or may not reflect reality, and again, you could make the model more complex. Okay. Now, you will notice that as I type things here, this keeps on changing, and the values change. And that is because it's doing a random number, and Excel makes a random number every time it takes a new random number or set of random numbers every time you hit a new key. So what we are concerned about is we are going to be concerned about how does this affect things on average. And I guess I'm a little bit ahead of myself. We'll get there in a moment. But before we get there, we want to look at what happens with the harvest. And we are going to change our harvest. And so if there is a storm, we are going to take into account the volume harvested as normal here. But we're also going to assume that we are going to harvest anything that got destroyed by the storm. And so we are going to be doing the sum product of our volume here times the amount of loss here. And so that gives us the amount of harvest. And again, a crude model, it's basically assuming that if it is destroyed, you're actually going to be able to salvage it all, which may not be the case, but that's what the modeling assumption is for this. Okay, then when we take the net present value, we are going to take into account the price here times the amount harvested. And we're going to take into account, as we did before, the cost of reforesting that land that has been intentionally harvested. And then we're also going to take into account a cost of reforesting and rehabilitating the land that has been affected by the harvest. And in this case, again, it's a simplifying assumption. We are going to assume that the cost of rehabilitating that land is twice the cost that it would be if you actually harvested that land intentionally. Okay. And let's see, I think we've got that. Yes, and I misspoke. We are assuming a salvage rate not of 100%, of 25% in this case. So that is our S here, our salvage rate times the volume per each of those acres that have been destroyed. All right. So there we go. And then finally, let's see. Finally, one last piece of risk. And let's suppose that the price that you can receive, it is based on that downward sloping demand curve. But let's suppose that there are other things that are going on in the system that can cause the price to be as much as 25% above the normal predicted average price and as much as 25% below the normal average price. And so we could take that into account by taking another random number here. And that random number is going to be something between 0 and 1. And we're going to multiply it by 0.50 because it can be as much as 25% below up to 25% above the median price. And so that gives us our 50%. And the median price then is going to be, we're going to add that to 75. So if R is 1, this becomes 0.5 and it becomes 1.25. So it's 125% of the normal price. And if R is 0, this becomes 0 and this becomes 75% of the normal price. And so we get between 75% and 125% of the normal price there. And so we can see that that one has been coded in here. And so we are taking our random number, multiplying it by 0.5, adding it to 0.75, and then multiplying it by that 541 that we had before, times the amount of volume that we harvest, raised to the negative 0.07. And so there we have it. And there's our price risk. And so here is our sheet that I've just talked through. And then figure 8 here is looking at trying to get a sense of what the variability is that is potential given different runs. And so we're going to run this model 100 times. And again, we are going to do that by setting setting up a table using our table tool. And so here we're going to set this to 014 here. And so we want to know the amount of carbon. And then you can set this up for net present value too, and you can adapt this, but we want to know the amount of carbon here in the forest. So there it is. Notice that with damage here, the amount of carbon is lower in this case at the end than it would have been without taking into account the storm damage. Then here, we're going to get rid of this again so that it can calculate. So we're going to run 100 simulations here. And so this goes down to 100. And we are going to select then X3 down to AD 103 here. And we are going to go to our data, our what if analysis table data, and our row input is going to be cell I16. And so we want to set I16 here. So again, we are looking at different rotation ages, but notice that this is now in rows here. And then our column input, we're just actually going to select a random cell. I say to do it in P1 But really all it's doing is a cell that doesn't have anything in it, because I don't want to vary anything in the columns. I just want it to iterate through and give me 100 simulations. And we should be able to hit OK. And there it goes, and it's plugged this in, and it's saying that if we have a 10-year rotation, the first time we use a 10-year rotation, we get 16,000 tons of carbon on this forest. The second time, if we used a 10-year rotation, we get 16. And basically, with a 10-year rotation, it's always 16, because if a storm damages it, we're harvesting it all every time. It does start to vary if we use a 20-year rotation, because sometimes there's a storm and sometimes there's not. And then there's a lot of variability out here with at 100-year rotation, because there are different numbers of storms, but you're likely to get some storms that will reduce your carbon. Then we can do some summary statistics here, and we can look for the max amount of carbon that is in, if we used a 10-year rotation. And similarly, if we use a 100-year rotation, with a 100-year rotation, it looks like the max amount of carbon is 105 tons. We can look back here at our carbon here at 100 years, we have 105 tons here. And so what that is basically telling us is that occasionally you have a year when you have no disturbance whatsoever. But the minimum here, with a 10-year rotation, it's still 16. And we can go back and look at this and see there's 16 tons with a 10-year rotation with no stochasticity. That is the max and the min in this case. The mean, then, we can average, and as might be expected, the average of the 10-year rotation is 16. But if we look at the average of the 100-year rotation, okay, it is, in this case, it's going to change some. It's 79, but if I change it again, went to 77, so it'll change a bit. We can look at the standard deviation of those, and now we're going to calculate a standard error. And so here we're calculating a standard error. And this is 10, because the standard error is based on 100 iterations, and so the square root of the number of iterations is 10 instead of, it's 100. Square root of 100 is 10. Okay, and then we can calculate the 95% confidence interval here. So it is going to be, we're going to approximate t as 2, because it's a fairly large sample size. You could look up in a t table what the actual exact t is for the 95% confidence interval, but 2 is close enough for our purposes. At infinity, you'll recall it's 1.96. But frequently we just use 2 to simplify our calculations. So that's what we're doing here. And we're going to multiply that by the standard error. And so we get, this is the width of the confidence interval here. And the reason this becomes important is we can set up a graph like this, and we can see with stochastic storm damage, with stochastic prices, then our table here is looking somewhat different than the figure here. Okay, so this is telling carbon, this is telling net present value. When we come down here with stochasticity, the amount of carbon on average is down a bit from what it would be with a 100-year rotation. and the amount, the optimization of net present value may change a little bit. And certainly we have some range that we would expect with these different different rotation ages, because of we're taking into account the fact that sometimes a storm is going to hit and sometimes a storm is not going to hit. Okay, so that's the end. This is a complicated one. Please come in and participate in the Zoom sessions. Please feel free to use my office hours. Please feel free to work collectively and send me emails. This is complicated. It is introducing some new concepts in terms of the stochasticity and risk. It's also building on a lot of the concepts that we've been building up over the whole course of this semester in terms of looking at how to use Excel to model growth and yield, how to use those models to develop harvest plans, and to look at how to use area and volume control. It builds on the economic analyses we've been doing. So there is a lot going on in this lab. It's really, I expect it's going to be kind of a challenging one. But if you get this and you really understand what's going on here, you really understand a lot of what we've been covering for this entire semester. So, bit of a challenge. I certainly wouldn't have given you this one on week one. Hopefully you've come a long way since week one in terms of your ability to handle these things, but there's still more to learn, and this is actually relatively simple compared to the types of problems that you might face if you actually get hired on to be the planner for a large timber products company. But at least you have the basic skills, you have the basic understanding of how these things work. All right, so I look forward to seeing you in a lab session or office hour session. And again, reach out if you have issues.